Hi, thanks for the introduction. Thanks for the conference organizers for this opportunity to talk here. My name is Nicholas. I studied computer science at the RWTH Aachen University some time ago. I began building autonomous robots at the Roboter Club Aachen starting in 2010. And from this project, we created a C++ library known as modem.io, which is a C++23 library, which supports a lot of Cortex-M devices. And that's really where I gained all of this Cortex-M knowledge that I'm going to show you in this talk. I then started working at ARM on Cortex-M sandboxing, so even more Cortex-M content. And then I got bored of that, and I went back to university to build a digital railway signaling system, because you can only do that once in your life. And then I finished my master's degree, and now I work at Auterion, debugging the open source PX4 autopilot for commercial drones. So the PX4 autopilot runs on the Skynode, which contains a Linux system. You can see this on the right here. And it also contains a flight management unit, which is the red rectangle. And this runs PX4 on an STM32H7 with a lot of sensors. It's based on the NuttX RTOS, which is fairly complex, and we use a lot of its features. And it has some subtle bugs also. And my job is to debug this, to debug PX4 and NuttX. And it's difficult because it's a large code base, and it's a very fast processor, 480 megahertz. So you don't get very far with printf debugging. You actually need to do some real-time tracing, and you need to use the debugger properly. So I want to share some of the tools that I wrote over the last few months to help me debug. Remote debugging on microcontrollers requires some extra steps. So you can see the microcontroller on the bottom right here. You need to connect to the serial wire debug signals to a hardware debug probe, for example, J-Link or an ST-Link, which is a cheaper version. And then this debug probe communicates over USB to the driver software. Typically, this is OpenOCD or J-Link GDB server. And this implements the GDB server protocol. And then GDB connects to this GDB server with a local TCP connection. And now you can already debug your microcontroller in the command line, which is not very user-friendly. So typically this gets wrapped by the GDB machine interface inside your IDE. And that actually then shows you a visual representation of the entire debug state, where you can set breakpoints, you can single step through the lines. It's much more user-friendly. But it's not scriptable. So we're not going to do the IDE route. We're going to go through the command line, and I'm going to show you a couple more tools, how to make that more useful, and also how to script it from the outside for unit testing and for CI. So extending GDB is possible with the Python API. GDB actually has its own scripting language, but it's quite limited. So the developers thought, let's just extend it with Python, then people can do whatever they want. So you can source Python scripts inside GDB using the source command, and then you can import GDB. This Python module only exists inside GDB. There is no Python source code for this. It is directly implemented as a C API in GDB, which is fun to debug if you want to debug the debugger. And there are several limitations, like the Python API cannot write variables. You must execute the GDB scripting language from inside Python. So that's annoying. You cannot access all of the debug information. Some stuff is missing, like the C preprocessor macros are missing, which is annoying for NuttX, because NuttX uses kconfig and then a lot of macros to configure everything. So that is not accessible inside GDB. But it is very well documented at an API level, but unfortunately it's not trivial how to do things that are more complex. So you have to read the source code sometimes, and there aren't that many examples out there. There are some tools inside the NuttX repo, which is helpful. And finally, the API, the Python API, is language independent. So it works for C, C++, but also for a bunch of other languages. And so the semantics are sometimes a bit weird. Like you don't have pointer semantics, for example, in Python. So it's not properly exposed. We wrote I wrote the debug tools using this API. There is an open source project called the Embedded Debug Tools mdebug. It's BSD licensed. It's fully open source. It's available on GitHub. And it is highly modular, so you can reuse it, even though it's specific for PX4, NuttX, STM32 combination. Feel free to contribute or just open up issues or look at how this works. Okay, so enough talk. Let's look at some GDB tools. The very first tool is something that NuttX has itself. NuttX also has a Python plugin called the threads info threads. I think that's what it's called. And it looks at the RTOS. So we extended that in PX4 using timers to get the CPU usage information, which is not standard in NuttX. And this requires us to rewrite this tool a little bit. So you can see here the PID, the name, the CPU, the stack usage, and most importantly, what it's waiting for on a semaphore, for example, or a signal. This works by implementing a custom GDB user command. This is sort of the very small scaffolding, the very minimal scaffolding here. So GDB can look up global symbols. It can also look up symbols in other scopes like functions or files. And NuttX uses a so-called ready list for tasks, which is this G pending tasks pointer, global symbol, which contains a linked list. And we just walk that linked list in this plugin. And some of these properties, like the name, you can just read directly from the TCB. The TCB is the task control block. But other things you need to compute indirectly. Like if you want to compute the stack usage, you need to implement a binary search to find the watermark. If you want to look at the CPU time, you need to look at timers, STM32 timers. So the complexity here can be scaled up or down. There are also RTOS plugins for this, for the debug probes, but in my experience, they were quite fragile. And also, there isn't really that much advantage over just implementing it in GDB. That's why we've just implemented this in GDB. Let's look at another example. NuttX implements its own dynamic interrupt dispatcher in assembly, which is a bit annoying because every interrupt handler inside the NVIC interrupt table is the same function. So that's not particularly useful for debugging. So I wrote a small tool that just looks at the NuttX dispatch tables and then renders it. You can see here the priority, which is of course all the same because NuttX doesn't support nested interrupts. But you can also see if the interrupt is enabled, pending, or active. So for example, here the RAQ59, the DMA interrupt is active. You can also see what argument it had. And the RAQ65 just below that is pending. E stands for enabled. So E, enabled, pending, and active. So this is super useful to figure out what functions to put breakpoints on. But of course, it is specific to NuttX. There are also some hardware-specific tools that we built. So STM32-specific tools. I often need to know what the state of the microcontroller pins are. So this tool shows them to me. You can see the pin name, the configuration, the input and output state, the alternate function, the signal names, which are our names that we call the pins, and their functions. So for example, the pin A6 and A8 are inputs with a pull-up, which are currently high. You can see the config is abbreviated. And pin A13 and A14 are the debug connection, the serial wire debug connection from which we're currently looking inside the pin. And they're internally connected to alternate function 5 and 0. And the data connection here is also configured for a very high data rate plus VH. So this is incredibly useful, of course, for just looking at the internal state. You know, like any microcontroller is a logic analyzer if you just debug it hard enough. So it would be nice if you could generalize this because the GPIO, of course, is a peripheral and it has registers, and I'm just writing a custom plugin, but of course that doesn't particularly scale. So it would be nice if you could have a generalized viewer of peripheral configurations. And this is exactly where the system view description files come in. They are a standardized XML format that describes the register map, so you don't have to copy it out of the PDFs, which is really annoying. The STM32 SVD files are a little broken, but there are manual patches available. And there's already a great GDB plugin from Pengy that does the heavy lifting for you. So it loads the SVD files and it tells the debug probe to read the right memory and convert it into a structured form. And we just wrap this functionality. So this is how it looks like. You can see here that we're looking at the DMA2 stream 0 configuration register, S0CR. And you can see the raw binary register value. And then below, you can see all of the bit fields broken up into their name and their description. And this is extremely helpful for just quickly checking the configuration of a peripheral without having to manually look at hexadecimal values and then look in the correct PDF and find the right page, which is super annoying. So you still need to check the reference manual, of course, for the big picture functionality of the peripheral. But just if you already know the peripheral, just looking at the configuration is super helpful. And then you can combine this with hardware watch points. So the Cortex-M has a mode where a data writes to a specific memory location trigger an interrupt. And so you can watch certain memory regions for writes and reads. And so, for example, here you can actually not single step through the code, but single step through the writes of a register. So here the stream 0 register is being watched, and you can see exactly what the difference is and what location in the code actually configures this. And PX4 is very large. It's almost 4 million lines of code. So for me to understand what is actually happening, these kinds of tools are extremely useful here. Unfortunately, on the Cortex M7, STM32H7 is using the M7. There is a bit of buffering. There is some write caches, and so sometimes the processor already executes instructions by the time the write arrives. And sometimes if you have a DMA that configures peripherals, that can also trigger these interrupts, and then you get weird backtraces. So that's just something to keep in mind. It's a hardware limitation. While we're talking about debugging weird things, because the NuttX interrupt dispatcher breaks the backtrace, there is a workaround for that. So you can enable the vector catch bits inside the Cortex-M. And then whenever a hard fault is triggered, or a bus fault in this case, the execution stops before the interrupt dispatcher. And then the stack trace is actually still intact. So you can see here a hard fault is triggered. The vector catch halts the CPU. You can see the ARM SCB is the plugin from Pengy, which looks at the SCB peripheral. In this case, it's where the fault registers are. So you can see here there's a BFAR, a bus fault, which is valid. It's a precise error. And then because we have the backtrace, the exception frame exists there, the signal handler frame exists there, and then GDB can reconstruct the rest of the frame. So we can see exactly which instruction, if we look at frame 2, which instruction caused this bus fault, which in this case was a load instruction. And you can see the parent is 0, and therefore R4, the register 4 is 0, and therefore that try to load it register 0 plus 8 in this case, which is not available to load from. So this is extremely useful for finding things like that. NuttX implements core dumping. Whenever there's a hard fault, it renders a core dump for later things, but you can also implement this inside GDB. What you can do, it's relatively simple to do. You just read out all of the volatile memories, like SRAM, and the flash is already part of the ELF file, so you don't need to copy it. But what I've added here is all of the peripherals, because we have all of the peripheral register names and addresses inside the SVD file, so we can get a complete copy of the device, including all of the peripheral states. And this is something like 2 megabytes of data for the H7. It's not that much. We then pipe this into the crash debug utility from Adam Green, which pretends to be a GDB server. instead of actually being connected, it just pretends to be connected, and then that works the same way. All of the tools also work the same way. You can also look at the GPIO, even though the device is dead, because we saved the register file. NuttX actually does something slightly smarter than this. It generates an ELF file, which is natively read into the ARM non-IABI, into the debugger, which is unfortunately relatively annoying to produce. So I'm still going with the crash debug. It's simpler, way simpler. It's also fairly undocumented. Unfortunately, a lot of these tools are quite undocumented. So NuttX also has its own crash debug implementation, which is called the mini dump server. Okay, so now that we have all of these tools, maybe we want to do something cool with them. I talked about CI. We want to be able to find certain bugs and then write unit tests to make sure that they don't occur again. So instead of doing this inside of GDB, we're doing it from the outside of GDB, and we're using this machine interface that is typically used by the UI, by IDEs, in order to provide you with a graphical representation. So here we're using Python to do this. So we're writing a Python script which launches GDB in the background and the debug probe in the background. And in this case, we systematically fail. We have a small patch that systematically fails the malloc call. So if on the nth malloc call, it just returns a null pointer, and then we can see which code actually causes a hard fault using the vector catch mechanism and the backtrace mechanism. And as you can see here, if there's a hard fault occurred, we call arm scb, and then we execute the backtrace, and we save all of this for later. We also have an N-shell implementation of this, so we can also interact with the N-shell on the NuttX shell interactively inside these scripts. So we can really control the whole system here. And then we can convert this backtrace to a graph. And you can see here all of the reasons, the locations of a hard fault when a malloc call returns null. You can see the memset function down there, which unfortunately got past a null pointer. It wasn't checked before memset was called on it. So if the malloc failed inside the UARP implementation on the bottom left here, then memset tried to write to location 0, which of course isn't great. But it's super easy to find these kind of bugs if you just automate them. You just crawl through the entire source code, the first 30 seconds or so of malloc calls. It's like 4,000 malloc calls in PX4. So it's much easier to test and fix these out-of-memory conditions with GDB scripting. That's just one example. We also have logic analyzers attached that try and inject failures, and then we see, okay, what actually happened here? Like if an SD card write, for example, failed, does that actually cause issues, or is the error recovery working properly? Unfortunately, all of these tools require the CPU to be halted. And if you're writing an autopilot, you're typically flying in the air. And so if you try and halt a drone inside in the air, then you tend to crash. So it's not super great to do that. So there are also debug tools that use profiling, non-invasive profiling, real-time profiling. Typically, the simplest profiling method is logging, usually over a serial link, which is very low cost. It's very effective. Everyone uses it. Unfortunately, with a processor that's 480 megahertz fast, you will generate a lot of events, and it's not super trivial to get that out of the device. And it also creates a lot of overhead, particularly printf is not fast. So NuttX obviously thought about this tool. They have a real-time profiling system, the NuttX task trace system, which is implemented via hooks. It logs everything to SRAM and then to an SRAM buffer, and then it flushes this to a file. And this renders very nicely in Trace Compass, I must admit. It's very cool. It's a very cool feature. Unfortunately, I'm running an ARM64 Mac, and trace compass tends to segfault a lot. Making it practically impossible to use. And this also runs on the device. It adds a lot of flash, and it also takes a lot of CPU time. So we don't really have that. Our flash is always full with lots of stuff. So there is an alternative called the real-time profiling by Seger. Seger calls it System View. There's also a tracealyzer implementation of this where you just log to SRAM, and then the debug probe polls the SRAM and reads it out. So this ring buffer in SRAM, instead of flushing it to a file, the debugger does it for you in the background, which saves you a bunch of code space. But of course, the debug connection is still limited in its bandwidth. And there's also, particularly with Seger and Tracealyzer, these are custom GUIs with proprietary closed source licenses. And in particular, there's no NuttX support at all. So I don't know why they support every RTOS on the planet, but just not NuttX. So we had to implement our own. We use the built-in hardware in Cortex-M, which does the serialization, and in particular, it also does timestamping with cycle accuracy. It's implemented in hardware, so you don't need to actually have any code overview. There are 32 channels you can see here. They're called ports, and you can just write a 32-bit value to this, and then it gets multiplexed into a single data channel. And on the other side, we use the Orbcode project to demultiplex this single stream of bytes. And this is very fast. It has basically no overhead, less than 2-3% maybe in CPU overhead, and maybe like 170 bytes of flash for our use cases. So very, very little. The problem, of course, is that you're still limited in bandwidth. So you can only transfer about 3 megabytes per second, which is very fast, but it's only 3 megabytes per second. It's still enough for real time, but in order to visualize this, then you actually need a proper UI. We use the open source Perfetto UI, which is it's developed by Google for the Android tracing. It looks very nice. We've written a C++ tool based on Orbetto, based on Orbicolum. We call this Orbetto because Orbcode plus Perfetto is Orbetto. We're really good at naming things. And this is what it looks like. So this is, you can see at the top here, we've got the CPU, which is multiplexing all sorts of threads. And then you can see the interrupts below. And all of this is happening, by the way, within the same millisecond. So this is real time, right? So every tick here is 100 microseconds. NuttX really schedules a lot because it's a real-time operating system. So it's really, really educational to really see how this works. You can see all of the threads here on the left. We start a lot of threads in PX4. It also has the PIDs and the names. We have a lot of work queues for all of the sensors on the same bus, because if the bus is busy, there's no point having different threads. We just have a work queue. So all of this gets visualized. And yeah, if you zoom out a little bit, you can also see patterns appear because, of course, we're pulling the sensors every couple of milliseconds. Here, the tick, for example, each tick is 1 millisecond, so it's 10 times more data zoomed out. You can see the SPI buses getting read periodically. And then if you zoom out even further, every tick now is 100 milliseconds, you can see a hiccup. There was a brownout event on one of the sensor buses because too many sensors were attached, and there was a power glitch. And this is super easy to see in such visualizations because we are visual creatures. And so seeing something that's irregular is immediately fast, incredibly fast to spot. So this tool is incredibly helpful, and it's open source. So you can look at how it's implemented and maybe even use it yourself. Finally, we've also implemented heap tracking because you can track anything, right? I mean, you're not limited. It costs you so little to add some data here. that you can just add every malloc and free call, for example, to understand heap usage. Here you can see a single malloc call, which gives you the requested size and the returned pointer, including the overhead, because there is some overhead in the allocator. And by adding all of the allocs and by subtracting all of the frees, you can integrate the total heap usage over time, which you can see here. You could even do heap fragmentation analysis with this information and then fine-tune your heap algorithm, but I didn't find a good UI for this yet. There aren't that many memory area visualizers out there. But you could create a histogram of all of your allocations and then create like an optimized binning block allocator. So there are a lot of possibilities here. But of course, I haven't had the use case yet. It still works relatively well. But the single wire output, it's just a single pin, is again still limited by bandwidth. 3 megabytes is not a lot, and we are missing call stacks, as you can see here. So there is a parallel 4-bit wide data bus up to 1 gigabit per second. And in addition to all of the tracing information before, it also gives you a compressed instruction trace. So every instruction that is executed on the microcontroller, you can reconstruct on the PC. And then you get your call stacks. But this requires some custom hardware. So before, you can still use relatively cheap debuggers. Now you need expensive debuggers. The Orbtrace is an open source implementation of the JTrace, for example, which is much cheaper. It's like 10 times cheaper, so I strongly recommend it. It has an FPGA with a USB 2 connection, and it's incredibly fast to get it to work, and it works really well. You can get a lot of interesting information from the compressed instruction stream. You can derive, for example, the full stack traces. As I said, you can get the code coverage. You can get timing analysis, the complete RTOS state, branching information, and the goal is to combine this with GDB scripting and automated testing in the CI in the future. So this is not done yet. The current state looks like this. Quite hacky. You can see the Skynode FMU is connected to the Orbtrace, and it's transferring around 800 something megabits per second of debug information, which is great. So we're going to add call stacks to this, which brings me to the future work section. So in the future, I still want to support Trace Compass in addition to Perfetto, because Trace Compass has better debug tools. Perfetto looks very nice, but there isn't that much analysis you can do. I also want to add logic analyzers to Perfetto or to Trace Compass. So to synchronize external traces like I2C bus state, SPI bus state, Ethernet maybe. So that would be very nice. And of course, the parallel trace needs to be integrated. As I said, call stacks in real time, the entire RTOS state. And then something very fun, you can actually use the instruction trace, the branching information to guide something like American Fuzzy Lop, maybe in conjunction with a logic analyzer. So you can really inject failures in a systematic way and then see how the system reacts. Well, this is the end of the line. This is all the hardware and tooling that I currently use for debugging NuttX and PX4. In conclusion, debug all the things, use more GDB, use more debug hardware, and please test and contribute to the Orbcode project, play around with the Orbtrace, it's relatively cheap, fantastic probe. There are also a lot of very competent embedded people in the Discord channel, so if you want to learn a bit more about Cortex-M in particular, that's a good place to start. And please try out my embedded debug tools and look at them for inspiration. And yeah, thank you. And do you have any questions?
Hi, are you hearing me? Hello, hello. Are you hearing me?
Yes, I can hear.
All right. We have a question from the YouTube channel from Michael Jung. How good is Orbtrace working for code coverage analysis out of the box? does that integrate with GCOV?
I haven't tried it myself. So GCOV implements a hook inside the firmware, and then it outputs this over a serial line, which works well, but unfortunately it loads your firmware 2 or 3 times the size just because it needs to log every function call. You get the information out of the orb trace. How that's visualized, I don't know yet. It's definitely possible to do that. So JTrace does that. It's, I think, one of their main examples of just generating the heat map of instructions that were executed. It must be pretty easy. I don't know how well it does it out of the box. I haven't gotten there yet.
All right. Thanks for answering these questions. I would like is anyone here want to ask something? Can you go?
Yes, thank you, Niklas, for the presentation. Really interesting. One question from my side. I saw that you are talking a lot about ARM Cortex. Would this work also on RISC-V? Did you try anything on RISC-V?
I haven't tried anything on RISC-V, but I know that RISC-V has similar hardware features for tracing, at least. So it's called differently, of course, and they use different low-level protocols, but it basically works the same. The GDB plugins will probably just work because GDB abstracts the underlying architecture, the instruction set. So using the Python API is already high level. So you will get all of this tooling to work. Of course, STM32 specific tools will only work on STM32, but it's not super hard to implement this for RISC-V.
Do you have plans to make an agnostic implementation and then to define the lower parts architecture specific, or?
No, I don't think. No, I think it makes more sense to think of it in terms of software interfaces. The NuttX RTOS symbols and names and functionality will work the same on RISC-V as it will on Cortex-M. So that there's still a linked list on RISC-V. So all of this stuff works the same. But of course, you can display threads, for example, in other RTOSes, right? FreeRTOS has threads as well. Mm-hmm. So that would be the interface to port to. When it comes to GPAO, you would obviously have to port the platform. But again, the interface is more about pins, which is relatively standardized by now. I mean, pins, there's not so much difference you can do here. But like the real interesting stuff is like DMA engines or cross-trigger devices, which are like super specific to a device, and that will become difficult to port. It's difficult to generalize that. So I'm not going to do any of that, mostly because we only use STM32. We use an F7 and an H7. So those are currently the 2 devices that are supported. But I did make sure that it works for NuttX, for some of the NuttX examples. So you don't, at least it doesn't crash if you don't use the PX4 editions, because like the CPU timer stuff, that should work. But I mean, it's Python. Feel free to adapt it.
Cool. Thank you for the explanation.
All right. Guys, I directed the camera for the speakers so you can see us when we are not presenting here in person. And we have some questions here from the classroom. So I will pass back. Please introduce yourself. And
hello. Can you hear me?
Yes, I can hear you.
Hello, I'm Flavio, and very nice presentation. And I would like to ask you if maybe I do not understood correctly, but have you ever had a chance to work with J-Link as the debug technology for debugging using
Yes.
NuttX and PX4?
Yes, absolutely. So the debug tools support both J-Link and ST-Link and Orbtrace as debug probes. And JTrace. So that's fully abstracted.
No, okay. Yeah, because I worked sometime in the past with J-Link and it worked quite well. And straightforward for at least for standard debugging. Yeah, for let's say break points and read the registers. Yeah,
No,
I don't recall hard faults actually, but for a standard, let's say standard debugging working on the NuttX, it worked well with J-Link. Yeah, I was not able to use OpenGDB, but yeah, for J-Link it was quite nice.
Yeah, so we use J-Link for proper debugging. Unfortunately, J-Links are relatively expensive, so we only have a few of them. But the ST-Links that I showed you in the beginning, hang on, I have a slide. These ones on the bottom, those are really cheap. They only cost like $12, including tax, and the J-Link above costs like $400. So we typically just put a debugger inside a drone forever because it's so cheap, and then we don't need to. We can just connect with USB-C to the debugger, and that works well. But J-Link is faster. It's more optimized. I don't know. They do some magic there, but it's just faster and it's more reliable. So yeah, J-Link is supported. Absolutely.
I'm sorry, I think we missed the microphone, but it's back again. I have a question too, Thiago here. Does the NuttX instrumentation system allow you to develop a customized instrumentation for your application, for instance, or it's more for the OS structures like the context switching, semaphores, and so on? Do you know anything about it, Nicholas?
Yes, so NuttX has its own scheduling hooks called the Sched nodes for scheduler nodes, and we use those for most of the stuff. But then there are some things that are not instrumented. I assume because the need wasn't there, like the malloc implementation, for example, is not instrumented. So there is a patch set which is also open source. It's also part of this project. Which shows exactly the locations where you need to instrument this and how the logic works. So because it costs only a register write in each location, which is the timing again is done by the timestamping is done in hardware. So you really only need to write a register. You can put as many register writes as you want. It's basically free. So that's how it's implemented. So there are a lot more hooks here than are available by NuttX task trace system. And it's extendable. So I'm going to trace everything that is useful for me. Like if I need to instrument I2C or something, I'll just instrument it in the driver. Of course, it won't be upstream because it's it's garbage, but for my own personal use case, it's quite useful.
Does anybody else have another questions here locally? You? No? No? Can you check the YouTube channel if we have some other questions? Wait a minute. Michael's question was already answered. Well, in fact, I have a more generic question about these debugging tools and profiles. Could you highlight the most, as in your perspective, of course, the most interesting tools that you were able to use in NuttX that's not are present in other OSs or other systems, or you can't use in other systems? Because here we are talking from a university, a school, and well, the simplest debugging interfaces are printfs and GPIO toggling, or even JTAG and JLink is common, but it's not available for all kind of OSs, and it's even worse when we are talking about bare metal programming. So could you highlight the most interesting, the most useful tools you have been using with NuttX, please? In your perspective, of course, that's very personal.
I mean, using GDB, even without all of the plugins, is already a superpower. So if you can get a debugger on your device, even if it halts the CPU, just being able to inspect the current state of the SRAM, of the peripherals, is incredibly useful. So I think, like all of these plugins, they're helpers, but the foundation really is GDB. And please get an ST-Link, the cheap version. It's extremely capable. It can do tracing. It has an SWO input up to 20 megabits, which is fast. And it's super cheap, and you will not regret it. So having, I mean, it's also, particularly with Cortex-M, there's so much documentation online on how to get GDB to work, how to use it, how to use the commands. So I would say just being able to use the debugger is already good. You don't need to do any of this advanced stuff. This is complicated, and you probably won't need it. I mean, PX4 is a lot. It uses almost every NuttX feature. We have like 1,700 threads that we start. I think we only keep like 200 threads, but it's a lot. It's a lot, and you really need. I really need these tools. But if you have a simpler application, you probably don't. Just get GDB to work.
Nicholas, your presentation was very nice. Actually, I have a similar question like Thiago did about, did you compare, for example, the system view from JLink with other similar tools using the trace system already supported on NuttX, how it compare, and also Orbitrace as well?
Well, I mean, the system view doesn't support NuttX, so I wasn't able to get it to work. But I know that Trace Compass, for example, the UI has much better analysis tools with packet inspection and with list views. So Perfetto, I chose Perfetto because you don't need to install anything. You literally just drag a file into a web browser. It's a web-based tool. There are example files in the open source project where you can just drag it into your web browser and you can inspect the trace yourself. So that was the very interesting thing for me. Trace Compass is several hundred megabytes of Java, so that was a bit of an issue. But I mean, the specialized tools from Seger are probably going to be better. Also, Tracealyzer looks a little bit better. But what we're doing here is we really want to use this without a UI, right? We want to put this in the CI, the continuous integration, into our test racks. And how am I supposed to script a proprietary UI? I mean, this doesn't work. I mean, of course, you can like move the mouse pointer and click on things, but that's stupid. So, it was relatively clear also from the pricing structure of some of these tools that it would be more useful and cheaper for us to develop this ourselves and make it open source because, other people can use this tool.
Yeah, that is excellent because I always prefer make the open source solution give my priority, let's put it this way, because, we have recently the Unity 3D example. When it's a proprietary solution, they can change the price or they mind all the time. And when these open source projects like NuttX and many PX4 and many others, we have this guarantee that at least if something goes wrong, you have the source code, you can do what you want with. So it's always better to focus on open source. I think it's the most important.
It's also why we chose Orbtrace, the Orbtrace hardware, because at least I can look up how things work. It's the same with GDB. Like, there are proprietary debuggers, but some edge cases, some bugs, some seg faults, I can at least figure out why. And I can see it's not my fault, right? With proprietary software, that's always sometimes an issue. But yeah.
Exactly. Yeah, and I don't know if you remember, in the previous year, we have a presentation from the Dave Marple, the guy behind the Orbcode and Orbcode. Yeah, and he did a nice presentation about using NIT, and he's still doing great support in NuttX on new versions. And I just remember to send a message to him, asking him to show up here in the event, in the chat. I hope during the day or maybe tomorrow he show up, because he stayed with us since the first event, actually, and he was responsible for the first NuttX workshop in Gouda in Netherlands.
Yeah, he actually pointed me to this workshop, so I already know him, and so yeah.
Oh, yeah, that's perfect. So thank you very much, Nicholas, for this really nice presentation. And I'm glad you are here. And now we have this for the posterity saved on YouTube. So everybody that wants to learn more about it can play this video again and learn more from you. Okay?
Yes. Yeah, Thank you for your time.
Thank you very much for being here.